wedge girdle is constructed from 2 plywood sheets that are secured to wood members as its top and bottom. Okay. The allowable bending stress for the wood, okay, is 8 kilopascal, and the allowable shear stress is 3 kilopascal. If the fastener are spaced at 6 inches, each fastener can support 600 pounds in single shear configuration. Determine the maximum load P that can be applied. Okay. So when you have data like this, you have to step back to see what is the purpose of the data. Why they give so much information. Okay. Now that's learning. When you go and do engineering work, you need to know what data to take. Okay, what data to acquire. These are all given. Okay, these are all given. So now, why did they give stress allowable? And the question is really, really nice. They gave us stress allowable. Stress alloy. Seriously, Eugene? Normal stress allowable is equal to what? 8 times 10 to the power 3 psi. And this is for the wood. And we know that this stress allowable, they're being really nice and they tell us this is due to the bending stress. So the formula that we're going to apply over here is equal to mz over iz or iy. Could you remember? Iz, okay? Multiplied by y, okay? So this is for failure of the wood. Normal stress acting in the wood. Then the next one, they gave us stress, shear stress, allowable, and this is equal to 3 times 10 to the power 3 psi. Okay, and this is also for the wood. And the formula we're going to write is equal to shear in the y direction. This is equal to, not shear in the y direction, come on Eugene, wake up. Shear force in the y direction over IZZ QZ divided by T. This is due to the failure due to shearing stress. Okay. And for this case, we know, right, looking at the structure, we know that it's going to fail at the where? Centroid. If it's going to be the wood, it's going to be at the centroid. Okay, so it's going to fail at the centroid due to shear. Okay, at centroid. Failure at centroid. Okay, now the next one is the fastener are spaced 6 inches. 6 inches is a freedom of choice. You decide that you have a structure that is year distance and you decide to put 6 inches. Okay, you decide to put them 6. It can be 8, it can be 12. You decide. Okay, but remember, the wider the spacing you put means the less load it can carry. The closer means you have to keep on knocking the burger in non-stop. Okay, so you have to decide. So now the shear stress or the Q is equal to VQ over I, and this is equal to force that the fastener can support divide by spacing. Now, can anyone have any idea how they get 600? Anyone? How they get that 600? Before I go on, okay? Do you agree I'm very simple? Yes or no? Right? I'm very simple person. You give me food, you give me water, I'm happy. Okay? What I'm trying to say is this. Think simple. Okay? Even when stuff are really, really complex, think simple first. Okay? You think complicated, Marcel, we all go home now. Or we all let's go. Think simple. Okay, now, think simple. How did they get the 600? What will you do? If now I say, yes. Yeah. They will basically do this. They put the nail in, doom, 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 and they use a device, a piezoelectric sensor, and they pull it out and they measure the what? The force. Again, think what? Think simple. Right? So now I'm going to show you. Okay? How they physically pull out the nail, yes? How by pulling out the nail is related to your what? Shear stress. Right? How did they? So if we need to visualize this or not, we will ask ourselves, why are we calculating this for? Okay, now I'll draw for you what happened. Okay. So now you have a nail. Right? And the nail, remember I told you, we hammer this nail in. Right? So this is wood. And then what do? They pull the nail out and measure the what? The forces. They pull the nail out. So mechanically, pull fastener out and measure the force. Right? The mechanical pull it out. So that's where we get the 600. Then you ask me, Eugene, right? Sorry, you find me weird. I usually talk to myself. I do, okay? My wife find me really, really weird most of the time, okay? So now you ask yourself, Eugene, you just say it pull it out, and then if you see how the forces are applied, right? It's normal to this surface, yes or no? It's normal to this surface. Right? It's normal to this surface. How is this related to shearing stress? Right? How is this related to shearing stress? What is holding the nail back is a shear force. The shear force is acting in this direction. This is the shear force that is resisting the what? The pull out. Agree? Right? So that is the resistance. That's the resistance. Okay? I'm getting excited again. Unbelievable. Right? This is the what? The resistance force. Right? Then now, if I were to put, so why are we calculating the shear flow or the shear stress? Right? So if now I put an element down here, okay? And I draw the element in 3D now. Okay, so this is my X, Y, and Z, right? So what we want to find, I'll draw a bigger box. My thousand apologies. I draw a bigger box. My thousand apologies. So why are we calculating, right, shear flow or shearing stress on this surface down here? What's the purpose? Okay. So this 600, where it's acting on the element, is acting down here. Okay. So if you look at that, that is shear on the texture plate is Y, and this is X. Right? So remember, I taught you this quite a while back, right? Why are we analyzing on this surface that I'm highlighting in red now? Why are we analyzing this surface? Because the shear stress acting on the X plane Y direction is equal to the shear stress Y. Can you relate it now, please? Can you visualize it now? Okay, I'll explain again. Okay, I'll explain again. I'll let you guys finish talking first. I'll explain again. Okay. Okay. Let me build up the scenario for you. Okay. Are you all ready? No more copying. Copy later. Okay. Watch this. What we want to find out is how much force to pull this nail out. Now, you can do this on your own also. Okay. You only need to have a piezoelectric sensor. It's about $300 that when you or a spring gauge. Okay, you use a spring gauge and you pull out the nail, you can see how much forces. Okay, if you cannot get the information, think about simple ways to get the data out. Okay, so when you pull, right? When you pull, the resistance force is this direction. Okay, it's holding the nail down. Okay, right? Now, question for you. Does the length of the nail matter?
Gene, your
Yes.
voice is muffled.
Yes, I'm hearing you.
Your voice is muffled. We can't hear you properly.
Okay, I think it's my clothing. Sorry, thank you for telling me. Does the length matter? If you look at friction, is there cross-sectional area in friction? Mu equal to FR over Rn. No, right? The length does matter up to a certain extent. Up to a certain length, it does not matter anymore. Okay, once you pass that length, a critical length, how much longer will not matter a lot. If it's very short, yes. Okay, so now, when you go and build your deck, you ask yourself, all the nails in Home Depot or Lowe's come with what? Different length. Okay, it is true, the longer the length, you have more resistance. But at one stage, up to a critical length, it's going to plateau. It's not going to increase anymore. Okay, so now, how does this force over here affect our calculation? So we know that that force is going to generate a shear in this direction over here. Okay, it's going to generate a shear in this direction. So we know based on equilibrium, okay, shear xy is equal to shear y. That's why we still calculate what's happening on that surface. Okay, now that is enough theory. Now let's solve this problem. Okay, now let's solve this problem. So I'm going to get this diagram again, get the numbers. And let's calculate something that you have not calculated before. Okay, now let's do the first stage of failure. Okay, so we go for failure. Okay, failure. We're going to do, I'll call this mode 1. Okay, mode 1. Failure due to the fastener. Okay, failure due to the fastener. Okay, and from here, I'm going to do very quickly the shear force diagram. The shear force diagram is going to look like this, and this is P over 2, and this is minus P over 2. Okay, because A is P over 2, AY is P over 2, BY is also P over 2. Symmetrical loading, symmetrical both in loading and in terms of what? Geometry. Okay.